For the next question, again we have to define um, certain stochastic processes and their properties. First one is a wide sense stationary process. We say that a real stochastic process x of t is a wide sense stationary process if its expected value is a constant and the autocorrelation function depends on t1 minus t2 only. So WSS uses just the mean and autocorrelation, and they are easier to get than the second order density, and uh, we can do things like state state estimation, parameter estimation, prediction, all of this in the mean square sense. And instead of paying more attention to specific value of the stochastic process, we concentrate more on the power of the signal. The autocorrelation function at t1 equals to t2 is the average power of the signal at t1. And for a stable LTI system, if the input is WSS, the output is also WSS. Next is the independent increment process. It means that x of t1 minus t2 and x of t3 minus x of t4 are independent if they are on non-overlapping intervals. Independent increments implies uncorrelated increments. Um, Poisson process, Wiener process, random walk, they're all independent increment processes, and independent increment, it's related to the Markov process. Next one is the Markov process. We say that a process is a Markov process if the past, the statistics of the past has no influence on the statistics of the future if we know the present. And we know that the Poisson process, Poisson impulses, semi-random telegraph, random walk, Wiener process, they're all Markov chains. Next is the normal process, which is also the Gaussian process. And we say that a process is normal if the random variables x of t1, x of t2, and so on, x of tn are jointly normal for any n and any time. Uh, the statistics of a normal process is determined in terms of its mean and autocorrelation, and the mean is a function of time, and we've taken normal process as a property of stochastic process. And for example, a Wiener process and or a random telegraph signal, they are Examples of stochastic processes. So the normal process is taken as a class of stochastic processes, and the other examples which I mentioned, they are taken as specific kinds of stochastic processes. Uh, Next is the uh, s- strict sense stationary process. Uh, we say that a stochastic process is stationary in the strict sense if the statistics is not affected by a shift on the time axis. It means that x of t and x of t plus e have the same statistics for any value of e. Now we have to explain white noise. Uh, a general white noise would be, say, um, we have a stochastic process v of t, which is dw of t by dt, where w of t is a Wiener process. The stochastic process is said to be a white noise if it has zero mean and an impulse autocorrelation function, that is r of t1 comma t2 is q of t1 into delta t1 minus t2. Uh, Next is the mean ergodic process. And we say that a process x of t is mean ergodic if limit t tending to infinity 1 by 2t times integral minus t to t x of t dt is equal to the mean of x of t in the mean square sense. And this value must be constant. So the mean must be constant, and the mean square sense is one kind of consistency, and there are other uh, in probability with probability 1 and so on. This must be seventh one. So the last one is martingale. We say x of t is a martingale if e of x of t given x of t is equal to x1 is equal to x1, where s is less than or equal to t. So it's pretty much the conditional mean equals the condition case, and it's true for random walk and the Wiener process.